Hi everyone, I am Priyadeep Shah. Today I will present the paper LoRA Low Rank Adaptation of Large Language Models for my course Natural Language Understanding. Okay, so before we get into LoRA itself, let's first understand the motivation. Why do we need fine tuning? When we pre-train a large language model on a huge corpus, think of a GPT-3 train on 100 of GB of internet text. The model learns very broad general purpose knowledge. It understands language, grammar, facts, reasoning, and so on. But here is the thing, for a specific downstream task like summarization, question answering, or converting natural language to SQL queries, the model needs to be adapted, and the standard way to do this is fine tuning, where we take the pre-trained weights and continue training them on task specific data. The method is very simple: pre-train once, then fine tune for each task, and this works really well. Okay, fine tuning consistently outperforms few shot prompting even for a model as large as like GPT-3 with 170 billion of parameters. Okay, next, but what is the problem of the technique full fine tuning? Let me put this into a perspective. For GPT-3, that's 170 billion of parameters. Each fine-tuned copy takes about 350 GB of storage. Now imagine you have 100 different tasks. So 100 into 30, 350 GB, so is equal to 335 TB just for storage. And during training with the Adam optimizer, you need roughly 1.2 TB of VRAM. That's an enormous amount of GPU memory. Also, every time you want to switch tasks, you have to load different model weights. Mathematically, you are going from pre-trained weights 50 to 50 plus del 5, where the update is as large as entire model. This is clearly unsustainable. Okay. So some of techniques exist before LoRa. One is the adapter layers. The idea is simple. You insert a small bottleneck layers between the existing transformer sublayers. The input gets projected down to a small dimension, pass through a non-linearity, and then gets projected back to the original dimension. The key here is that only the adapter parameters are trained. The original pre-trained weights stay completely frozen. So there are two main variants, adapter L and adapter L and adapter H. Okay, so adapter L adds one adapter after the MLP and layer norm in each block, and adapter H which adds two adapter layers per transformer block. Both significantly reduce the number of trainable parameters. Okay, so there is some other things, prefix tuning. So prefix embedding tuning inserts trainable virtual tokens at the beginning of the input. Only these special tokens embedding are trained. The rest of the model stays frozen. And prefix layer tuning takes this further. Instead of just the input, it learns activation after every transformer layer, essentially replacing computed activation with trainable ones. And there is another very simple bit fit. It trains only the bias vectors in the model and freezes all the weight matrices. All of these the share common goal: reduce the trainable parameters while keeping the pre-trained model mostly frozen. But as we will see next, each of them has significant limitation. So why are not the existing methods are good enough? First, adapter layers add inference latency. These layers are processed sequentially, which breaks GPU parallelism. When you combine this with models sharding across multiple GPUs, adapters force expensive synchronous operation like all reduce and broadcast. Second, prefix tuning is hard to optimize. Performance changes non-monotonically as you add more trainable parameters. So it's not like that more parameters is equal to better. Also, the prefix tokens eat into your usable sequence length, which hurts the actual task. And the biggest issue, most of these methods fail to match the full fine-tuning baseline. You are always making a trade-off between efficiency and quality. So what is the full fine tuning baseline? So formally, if we define, the model start at pre-train weights 50 and gets updated to 50 plus del 5, where the update is as large as the original model. The training objective in NLP is same, maximize the likelihood. The full fine tuning gives us the performance ceiling. Adapter methods often fall short, especially on harder tasks. Prefix method underperform due to optimization difficulties, and LoRa is specifically designed to match or exceed this baseline while using far fewer parameters, and that's what makes it special. Now, the key insight behind LoRa comes from a fascinating line of research on intrinsic dimensionality. Researchers shows that parameterized model actually reside on a low intrinsic dimension, and another researcher extend this to show that pre-trained language models have a low intrinsic dimension. They can learn efficiently even when projected to a much smaller subspace. So if the model itself lives in a low dimensional space, should not the change in weights during adaptation means that del W also have a low intrinsic rank? We don't need to the update all D cross D entries in a weight matrix. A low rank update is sufficient, and that's the core hypothesis behind LoRa. Okay, before we go further, let make sure we will understand what rank means with a simple example, right? So suppose W is the 5 cross 5 matrix, means total 25 entries, but W is has a rank 2. Okay, so all 5 rows or columns are not linearly independent. Okay, only two linearly dependent independent columns or rows are here. So we can wrote W as a multiplication of two matrix 5 cross 2 and 2 cross 5, right? So in main matrix in W there is 25 entries, and if we convert into multiple of 2 matrix, that is 5 into 2 means 10 plus 10 20. Okay, so 25 entries to 20 entries, so we save 20%. Okay, so this is the you have to know before going to the LoRa's methodology. So LoRa assumes something. Okay, so what exactly does LoRa assume? It assumes that pre-trained weight matrix W are full rank. They need to be because they encode all the rich knowledge learned during pre-training. But and this is crucial for the change need to adapt to a new task. Del W has a low intrinsic task rank. These are fundamentally different things, the weight themselves versus the update needed. Okay, so instead of learning full D cross K update, LoRa learns a low rank decomposition. So we decompose del W to a BA, where B is the D cross R and A is the R cross K, and R is the very less than any of these D and K. Okay, so for GPT-3, where D is equal to 12.23K, even for R is equal to 1 or R is equal to 2 is enough. That's the remarkable. Let make what is the architecture of LoRa. The for modified forward pass is H is equal to W0x plus del Wx, and del W is equal to BA, so W0x plus BX. Here W0 is the original pre-trained weight matrix and it stays completely frozen, no gradient updates at all. For initialization, A is initialized with the random Gaussian distribution and B is initialized to 0. This means at the start of training, del W is equal to BA and is equal to 0. So the models begins exactly where pre-training let off. That's the really elegant design choice. The output del Wx is scaled by a factor alpha by R, where alpha is a hyperparameter. And here is the best part. At deployment time, you simply compute W is equal to W0 plus BA and merge it into a single matrix. There is zero additional inference latency. The model looks exactly like a regular transformer. The advantages of LoRa are really compelling. Let me list them out. Okay, so no additional inference latency. Since you merge BA into W before deployment, the model runs at the same speed at the original. Massive storage direction, as you saw the example in the matrix example, 5 cross 5 25 entries, but if we decompose we get only 20 entries and we save the 25%. Okay, also we save GPU memory savings, and most interesting, easy task switching. To switch tasks, you just subtract one BA and add another B dash A dash. You only swapping teeny LoRa modules while keeping the shared pretend models. And LoRa is orthogonal to other models, means you can combine it with techniques like prefix tunings for potentially even better results. So what is the problem statement of LoRa paper? Now the model is initialized to pretend weight 50 and updated 50 plus del phi. The core problem is that the number of parameter in pretend models and the updated models are same. Okay, storing and deploying many independent instance of such a large model is simply infeasible. We need a way to represent del phi much more compactly, and that's exactly what LoRa provides. So parameter efficient formulation, which is DIT LoRa. So the solution is to encode a task specific update with a much smaller set of parameters. So the del phi is equal to del phi, but the del phi is parameterized by theta, and where theta is the very less than cardinality of theta is very less than compared to the phi 0. The new training objective is the same, maximize the likelihood. Here we only change the parameters, right? So LoRa uses low rank representation for del phi. Okay, for GPT-3 with 170B parameters, cardinality of phi can be small as 0.01% of phi 0. Okay, that means we are adapting the model with just a tiny fraction of the original parameters. Okay, so now revisit the why existing solution are not good. Adapter layers introduce inference latency. They are processed sequentially, which breaks hardware parallelism. On GPT-2 medium with batch size 1, adapter layer adds 20.7% latency. Adapter age adds 30.3%. With model sharding, this gets even worse because of synchronous GPU optimization. Prefix tuning has optimization difficulties, and both fail consistently match full fine tuning quality. LoRa solves all of these problems simultaneously. So what is the formal LoRa formulation? One more time. So suppose you have a pretend weight matrix W0, which is the size of D cross K. We constant the update with a low rank decomposition. Del W is equal to BA, where B is the D cross R and A is the R cross K, and R is the very less than compared to D and K. So the forward pass becomes W0x plus BX. For initialization, A is sampled from Gaussian distribution and B is set to 0. So at start del W is equal to 0, and the output is scaled by alpha by R to control the magnitude of the update. Okay. Next, what is the limitation of LoRa? Now, after merging A and B into W, multitask batching is not straightforward. Different tasks are different A and B matrices, so you can't batch inputs for different tasks in a single forward pass. After merging, the workaround is to keep A and B separate and dynamically choose the right LoRa modules for each sample. but this adds more latency, which somewhat defeats the purpose. It's an open area of research, but for most practical scenario where you are serving one task at a time, LoRa works good. This is the some results from the paper. The author tested LoRa across wide range of models and wide range of dataset. You can see the wiki SQL, so sentence to SQL converter. Here it achieves 73.4% accuracy. Mm, sorry, 73.4 accuracy, where full fine tune gets 73.8% accuracy. And for the summarization task, it's also did better than the original full fine-tuning methods. Here you can see the checkpoints 350 GB to 35 GB, GPU memory 1.2 TB to 350 GB. So massive amount of reduction. Okay, also training speed also is faster. Okay, so let me wrap up with the quick summary what we have covered. Okay, so LoRa freezes the pretend weights and injects low rank matrices B and A alongside them. Only B and A are trained, which means drastically fewer parameters. At deployment, you merge BA into W, so there is zero extra inference latency. The model performs as if it were full fine-tuned. LoRa matches or exceeds full fine-tuning performance on wide range of models and wide range of dataset. Okay, the task switching is also simple. You just subtract the BA matrix, and for another task you just add another BA matrix. Okay, now that's the coding part, how we can implement LoRa. So first is the LoRa config. The first thing you do, define the LoRa config object. Here you set the rank R. In this example it's 16 and LoRa alpha it's 32, and the target module's parameter tells the LoRa which weight matrices to apply the LoRa rank low rank adaptation. Here we are targeting the query and value projection, means QV and Q and V. Okay, in transformer it's Q and V. Inside the attention layer we also set a small dropout of 0.1 for regularization, no bias training, and specify the task type as casual language modeling. Okay, and the second part is wrap the model. Next you load your base pretend model using the automobile for casual lm dot from pretend, and then you wrap it with get pep model by passing in the model and the config. This is the magic step. It freezes all the original weights and injects the LoRa matrices A and B into the target modules. You can call model dot print trainable parameters to verify that you will see something like 0.01% parameters are trainable. Okay, that's the whole point of LoRa. So for training we need a trainer, and we get from the Hugging Face. Training is completely standard. You create a trainer object with your own model, training arguments, tokenized dataset, and data collector. You can then you call trainer.train, and it runs just like any other fine tuning job, except behind the scene only the teeny LoRa matrices are behind updated. After training, you shape the shape with model.shape pretend LoRa output, and the shape checkpoint is incredibly small. Okay, and this is the most interesting part of LoRa. Remember the equation. Okay, H is equal to W0x plus Bx. Here exactly how it works. The class has two small linear layers, LoRa A with shape in F and R, and LoRa B with shape R and out F, both without bias. In forward pass, the input X first goes through the frozen base weight to get the base output, then separately X passes through A and then through B, that's the low rank path. and two the two are added together with the LoRa output scaled by alpha by r. Okay, so and finally at inference time you load the LoRa weights on top of the base models, base model with pep.model from pretend. Then you call model.merge and unload these fuses BA directly into W and giving you W is equal to W0 plus BA, which is the main equation of LoRa. And after merging, the model is standard transformer again with zero extra latency, no separate LoRa path, no overhead, just a single merge weight matrix. This is what makes LoRa so practical for deployment. Okay, so this is the full pipeline of the LoRa implementation. The Okay, thank you.
Hello everyone, my name is Ishani. Today I am presenting on topic hierarchical topic modeling and nested Chinese restaurant process. So let's start our presentation. To understand why we need HLDA hierarchical latent Dirichlet allocation, we first must look at the limitations of the standard latent Dirichlet allocation methodology that we have. In latent Dirichlet allocation, we face a major problem which was model selection dilemma. We have to tell the model exactly how many topics K exist before how many topics K that we exist before even it sees the data. If we guess the value of the K is too large, then the model tends to overfit. But if we choose the value of the K to be small, then it becomes the topics become vague in nature. So furthermore, even we have to decide the hierarchy of traditional methods which was rigid earlier. They required a fixed branching factor, meaning you must decide in advance that every topic has exactly, say for example, three subtopics. This is biologically and logically incorrect. In real world computer science and in many domains that we have seen so far, um, might have hundreds and thousands of subfields for a given document. General, for example, a document on politics can have multiple subtopics like parliament, then different subtopics can be present on that topic. So we can have general topic and we can have multiple hundreds of subfields that we have. So we need a model that adapts its shape to the data, not the other way around, that we have given the shape and then we provide the data. We need a model that adapts its shape to the data. Now moving ahead, let's understand what is the motivation that drives us to the that is the major motivation of our research paper that we have. So in real world, the open-ended data, we have open-ended data and it's constantly evolving. We need information abstraction. Information abstraction means the ability to recognize that knowledge is nested. Think of how we human learns. We understand the concept of science first at us when we are in a smaller class, in smaller grade, like in 6th 7th, we understand the concept of science. Then we understand and specialize in biology, and then further those who pursue further in biology or specialize further in biology, they understand eventually the concept of genetics. A flat model loses this context. A flat model, which is a flat, when we perform standard models which are flat categorization, they lose such hierarchical constraint. A critical secondary motivation that we have is statistical denoising. In hierarchy, the function words that we have, which we normally called as stop words, like the, of, or, under statistical pressure, that we in our methodology, these words move to the root node because they appear in every document, so they become a kind of common word. And the deeper branches in our methodology that are clean and specific words that contain specific meaning, high semantic meaning, and specialized terms remain in the deeper branches of the tree. Now let's understand the latent Dirichlet allocation algorithm. What we have. So before we build a hierarchy, let's start with the generative story of basic latent Dirichlet allocation algorithm. The LDA imagines that a document is born through two stages of random process. First, the stage that we have is we pick a recipe or distribution that we call. So this theta that we have is the recipe or distribution of topics for the document, and then for every word distribution we pick a topic label. So Zn that we have is the topic label, and from the recipe we draw a actual word Wn, which is the word of actual word that we have is Wn. Beta that we have is the word topic distribution, a word topic distribution which is the vocabulary that we have. So it is kind of a specific dictionary for that topic. So beta is specific dictionary for that topic. Theta is the distribution, how much distribution in the document is of a specific topic. For example, the topic is 70% sports, 30% politics, so that distribution is given by theta. Then we have alpha, which is a Dirichlet hyperparameter which controls the sparsity of theta, and Zn as we mentioned, which is the latent topic, and Wn is the actual word that we have. The formula shown here represent the joint probability for all these variables. The hyperparameter alpha that we have is a knob we turn to control the sparsity, essentially deciding if a document should be about many topics or it should contain just one specific topic. So this alpha is kind of a sparsity controller or a knob which tells whether the document that we have should contain lots of topic or it should contain little or some specific topic. Now let's move ahead. This is the explanation of the terms that I have mentioned here, theta, alpha, beta that we have, and the specific probabilities that we have. P theta given alpha shows that we draw a topic recipe theta from Dirichlet distribution. So we obtain this theta, which is our distribution of topics from the Dirichlet distribution, and then for every word in the position n in the document we pick the topic label based on our recipe, which is a distribution of topic that we have. Now once we have the topic label, we look at the topics dictionary, which is our beta, and the actual word and the topic that we have. So we have Zn and we have beta, and using Zn and beta we predict or we pick the actual word, which is Wn. So this is about latent Dirichlet allocation LDA. Now moving ahead, we will study Dirichlet distribution. So Dirichlet distribution is the mathematical heart of this model. It is often or mostly described as distribution over distribution. In HLDA, we use it as a prior to determine how to determine document divides its attention across levels of hierarchy. So in the equation we can see here, theta I represent the topic weights. For a 3-level theta, for example, the theta can be 0.7, 0.2, 0.1. So it sums up to be 1, and for each level theta is giving the distribution that we have, meaning the document is mostly general information with some field specific and very little that we have is niche content. The gamma function that we have act as a normalizing constant, ensuring that regardless of complexity, our total probability always sums up to 1. This we have as explained in the previously. This is about the terminologies that we have used. So gamma function that I mentioned was a normalizing constant which ensured that regardless of the complexity, our total probability always sums up to 1, and alpha that we have is a how many words we expect in that topic before seeing any data. So it's a prior belief that we use in our model. And then theta, as we discussed earlier, is about distribution of topic in that document. Moving ahead, now we will see our proposed solution. Our proposed solution contains nested Chinese restaurant process. So what is nested Chinese restaurant process? So imagine a case when we have infinite city of restaurant. Every customer, which in our case is a document. It starts at some root restaurant. Inside this we are picking a table is proportional to how many people are already sitting there. This is the popularity or rich gets richer effect. So when we consider a table, when we are choosing an existing table, so the probability that we have is mi being the number of customers that are already sitting on that table, and then we have this gamma, which is a hyperparameter, and m minus 1 is the total customers that we have seen till now. And when we are choosing a new customer, then when we are choosing the new customer, then we have this fixed probability that we have gamma, which is also called as innovation parameter, divided by gamma plus m minus 1, which is the total number of customers that we have seen. So this is the probability that we have when a new customer that comes in sit in an existing table, and this is the probability that we have when a new customer comes in sits in a new table, which is an innovation. So this gamma is also called as a innovation factor. Crucially, each table contains a referral card to a different table restaurant at next level. So by sitting at a table, the customer is choosing their path through hierarchies. This allows the model to sprout new branches organically as new data arrives without us ever specifying the number of topics, which was our major limitation in the previous models that we have seen so far. We have to specify the number of topics that that a given data should contain. But here our model organically understand as the new data arrive the number of topics it should contain. So here is also one simple example that is shown here. When the first customer comes, he sits on the first table. Now now on the second row we can see the second person has two options. The second person can sit on the first table. When the second person sit on the first table, the existing number of person that are sitting on the first table is 1 divided by alpha, which is our innovation parameter, and the total number of customers that we have seen so far, which is 1. So this is the probability if the second customer that we have chooses the first table. Now the second customer also have the option to choose a new table, and that probability that we have is 1 upon 2 plus alpha. Then comes the third customer. Now the third customer have two options. The third customer can sit on the first table, where the number of people that we have is 1 and the total number of people that we have is 3 plus alpha, or the third customer can sit on the second table, where the number of people that we have is 2 and the denominator becomes 3 plus alpha, or we have the third option also, that the third person can sit on the third table, sit on a new empty table with the probability of alpha 3 plus alpha, where alpha that we have, or gamma, which is also called gamma or alpha, is our innovation parameter, and in the denominator we have the number of customers that we have seen so far. So this is how the Chinese restaurant process that works. It allows to sprout out new branches organically as new data comes in without ever specifying the number of topics. So every time a customer comes, he has the option to choose between previously occupied cluster, or he has the freedom or the choice to choose a topic on its own, which is not used by the previously entered customer. Now moving ahead, this is Now moving ahead, we come to the generative process of HLDA. So this is the generative process in a proposed solution of HLDA, which is hierarchical latent Dirichlet allocation. So what is the process? So now let's putting all together, we will describe the generative process of HLDA. The generative process of HLDA follows three strict steps. The first strict step that we have is path selection. In path selection, a document traverses the tree from root to leaf based on the nested CRP that we have. The second method, the second step that we have in generative HLDA model that we have is level mixing. We draw a vector theta that determines how many words in the specific document come from the root, how many words that we have come from the middle or the leaf. Basically, we draw a vector theta, which was our distribution vector, which describes how many words that we have that belongs to different levels of the tree that we have. The third step that we have is word sampling. It means that for every word we pick a level and then we go to that topic node of that level, and our chosen path, we pick a word from that nodes dictionary. This a path constraint is vital. It forces the model to find a single consistent thematic genealogy for each document. So what it means that basically for each word in the n words in the document that we have, we first go to the corresponding level where that word is a corresponding level corresponding to that word, and then we choose one word from the topic distribution, which was earlier, as we described, was the dictionary of the topic, a specific word which we call as CDZN, CDZD, N. So this is the generative process of HLDA that we have. Now coming to the inference, which is the workout. Since we only observe, so inference part, so we have understood how the training or preparation of the model that we have, generative process that we have of our model done, it is done using the HLDA generative process. Now after generative process, we will discuss the inference process. So in the inference process, what happens is, since we have only observed the words, so now for inference we are using Gibbs sampling algorithm. So the Gibbs sampling algorithm should be able to work in the backward direction and find the hidden paths and levels. The sampler essentially here in this case asks two questions for every word. The questions are, which level did this come from and which path does this document follow? The decision that we have is a product of NCRP prior, CM, the probability of CM given CM minus 1. This is the formula. This is NCRP prior. It tells us that a given path that we have, is this path a popular path in normal language, or in definition language it tells us the structural property. It favors existing path unless the data strongly demands a new branch gamma. Then the second term in this formula that we have is marginal likelihood. It answers the questions of like, do the word actually fit the topic on this path? So as described, it finds the word fit test. So it uses a gamma to calculate the probability of documents word appearing in the topic along the path based on the prior word counts. Then at the end we have is the sieve mechanism. This sieve mechanism is in action. So if a word like let's consider if a word we have is neuron. So neuron appears, if a word like neuron appears, the likelihood will pull the document toward a biology path. So even if the prior for politics path is currently more popular, then also the likelihood for the biology path is higher, and that is why this neuron word will appear in the biology path. So this is the inference inference mechanism that we have for inference procedure that we have in Gibbs sampling. In Gibbs sampling, what happens is we first perform 10,000 iterations. These iterations are discarded. Just to ensure a random walk has reached the region of high probability, and once we have reached the region of high probability equilibrium, then we start the actual inference that we have. The Gibbs sampling algorithm is an algorithm which is based on MCMC algorithm, which is Monte Carlo Markov chain technique. What happens in this technique is that samples one variable at a time, which is level Z and level C, while the other variables that we have, theta and beta, we integrate out theta and beta. So this is the inference mechanism. Basically, in the inference mechanism, we have the words, and then from the words we start to move backward to find the hidden paths. For a given word, we find the hidden paths. That suppose we have the word such as parliament. So for this parliament word, we find what is the hidden path for this word. Second, for the hidden path, we also find the levels. These levels specify the topic. So Gibbs sampling is an inference algorithm that we are using, that helps us in moving backward. While in case of generative process, we move forward. We find the path, and then we found the words, and now we are moving backward. We have found the words, and now from the word we are checking whether this word belongs to this path, and then the levels or the topics associated with these words. This is what we have explained. Now let's see a workout example that we have. Since we only observe words, we must use Gibbs sampling to word backward. Now let's see a workout example that we have. As explained earlier, we are using Gibbs sampling in the inference. So how this workout example is explaining? First of all, we'll again see the formula that we saw earlier. We have the prior, which prior is based on NCRP. As we defined here, this prior is based on NCRP, which gives us the structural property of the word. And the second we have is the marginal likelihood, which find the word fit test. So we have this prior and likelihood. When these are multiplied, we get the assignment probability. So now let's see a workout example that we have. So consider we have a word neuron. So we have two possible paths. We have a path A, which goes from general to computer science. General is at level 1 or level 0, we can say, and computer science is at level 2. The second path we have is general. So in general, normally we have words which are common in all the documents. These are function words that we have described earlier, like the, and, is, must, and then we have the specific. In this case, we have a 2 level. So the second level that we have is politics. Now let's come to the prior. Let's say the probability of path A might be higher if there are more CS documents in the corpus. As we know, prior basically is based on the probability of the words that we have in document. So if we have more CS documents in our corpus, it means that the probability of path A would be higher. Then we have is likelihood. So how is we have likelihood calculated? The likelihood says that the neurons have 0.001% chance in politics and 5% chance in CS topic. So the result that we obtain is prior into likelihood will strongly favor the path A, which is general computer science, pushing the document in the CS hierarchy. So this we saw is a workout example. Now let's see a coding demonstration. So I hope you have clearly understood the workout example, that we have used the NCRP prior and we have used the marginal likelihood for finding the assignment probability. Now let's look at the coding that we have for demonstration of the code. So first of all, in this code we are using tomotopy library for implementation of our HLDA. So tomotopy library provides HLDA implementation in C++ and a Python interface for this. So we have obtained our data set, which is FH20 news group data set, which contains lots of news articles on different topics. Multiple news articles are present in this data set on different topics. We have defined our category to be science. Then we have recording, then sky space, which is basically science in space, science in medicine, science in space, and then we have politics. So these are the categories that we have defined. Otherwise fetch 20 news group contain lots of categories and lots of data. So next we have next the thing that we have done is we have done pre-processing. So in pre-processing, first of all we have removed the words which are having lesser than 3 length. Then we have removed stop words. These stop words are used for performing the pre-processing of the data. After the pre-processing of the data, we have defined our alpha to be 0 0.1. Then we have defined our gamma to be 1.5, which is our heart of NCRP. It controls the threshold or newness. By setting it to 1.5, we tell the model if a document does not fit existing branches, then sprout out or create a new one. That's why the model discovered in at the end we will say that the model because of this gamma value set appropriately was able to discover 96 topics autonomously without us setting the value of k. The model learned it on its own. Okay, so we have defined the depth 3 for our tree that we have. Then we are performing the training loop for 1000 iterations. 1000 iterations. In this 1000 iteration, we are performing the give sampler mover document, and the words between levels, and we are getting the paths and words that we have between the levels, and we are also printing the log likelihood. The model that we have stabilizes as the tree reaches a stable state. Then the model stabilizes, and after 1000 iterations are completed. So now let's look at the inference part. Once we have executed this code, so I hope you have clearly understood. We have obtained our data set, we have performed the pre-processing, then we have set the hyperparameters where we have set alpha 0.1, gamma which is our innovation factor, which is our gamma, which is an NCRP hyperparameter, which allows the model to create new topics if it does not feels like fitting into the previous topics that we have. So now we'll see the results that we have obtained. Rest of the parameters we have defined during the presentation what each parameters does. So now let's see the results that we have obtained. We can look at the topic 0. So in the topic 0, the words that we have obtained are there about what are very common words, because every document passes through the root. The model traps this high frequency low the model traps this high frequency low meaning words here, and this is automatic denoising of the algorithm. Automatic denoising is performed. Then we have level 1 categories. In level 1 categories, we have topic 12, which is about cars. So topic 12 we can see here. So it has cars, so it has words related to cars like miles, goods, sensor, light. Then after that we have topic 8. So topic 8 contains data like space, NASA, lunar. So this is all level 1 categories. In level 1, the tree branches out into 4 areas that we provided. The areas that we provided was space, politics, autos. So in that way the level 1 level 1 branches out. Now in the level 2, suppose level 1, this is the topic that we have, topic 8. So we have words like lunar, NASA, program, earth, which is as for the space topic. In the space topic we can see the topic 72, which is our orbit satellite, is separated from the topic 37, which is NASA space astronaut station. So these topics that we have, so topic 72 was more about human hardware and physics. So in the level 1 we are performing further separation. In level 1, which is our topic 8, was about space, we are performing further separation, which was orbit satellite, which is basically hardware and physics, while in the topic 37 that we have is more about human exploration. So it's like astronaut station. So we are further dividing it in the subtopics. As I mentioned, we are using Tomato Topi library for implementing HLD, for implementation of HLDA. So that I have mentioned that we have used here, and we can also see one more example of our code. So that we have is in topic 12 that we saw was about automobile. So in topic 12 also similarly, the topic 68, where the dealer, Saturn, car sell price, was separated from the topic 67, which is more about hardware or machineries of the automobile, like tire, brake, engine, fuel, system fluids. So in the level 1 also we are performing further separation based on the topics. So in case of space we did separation based on hardware or physics, and then human exploration. Similarly here in automobile also we are performing the separation. Now let's go back to our slides that we have. We have understood the code demonstration of our project hierarchical latent digital allocation and nested Chinese restaurant process. Now coming to the evaluation. Now let's come to the evaluation part of our code, evaluation part of our project. So to prove this works in the research paper, the author has used multiple strategies or multiple methodologies to show the results obtained by the research paper that we have. So first we have is the bars experiment. They created a document made of overlapping horizontal and vertical lines. As you can see in the figure B, HLDA perfectly reconstructed. This is a document which is having overlapping horizontal and vertical line, we can see. And of this horizontal and overlapping vertical line, the HLDA, which is our algorithm, perfectly reconstructed the hierarchy. It put the universal baseline at the root. It puts the universal baseline at the root and split the branches into horizontal and vertical lines. Quantitatively, the model achieves 70% of exact recovery for complex structure. So we have understood the evaluation on simulated bars hierarchy clearly. What was happening in the figure A, we can clearly see that we were having overlapping data, horizontal and vertical rows, and then after overlapping data, once this overlapping data was given to our model, this model clearly separated this horizontal and vertical lines. A universal baseline was created at root and split the branches into horizontal and vertical line, perfectly reconstructed the hierarchy of the data. Now let's move ahead to the next evaluation, which is quantitative structure recovery. In the quantitative structure recovery, this was performed on 50 different generated corpora, while with varying shapes. So in the previous model that we have seen so far, in the previous models, that we have seen, the models were not performing well when we had varying shapes of data, or we can say varying shapes of the trees. But our model works, performs really well, even if the trees that we have are varying shape. So here we have obtained that quantitatively the model achieves 70% of exact recovery even for complex structure. When it failed to get the exact tree, it was always within 3 nodes. Whenever the model that has failed to get the exact tree, it is always within the 3 nodes of the truth, providing an incredibly robust at finding the gist of the data. So our models perform incredibly robust at finding the gist of the data or the hierarchy of data, which is a main purpose or goal, and it provide a 70% of exact recovery, which is a really great result. Now let's move ahead to the next evaluation strategy that we have. The next evaluation strategy, we have perform a comparative analysis in this evaluation strategy. So what comparative analysis we have done? We are comparing our nested CRP and the base factor that we have. What happens in the nested CRP? We can see that the dimension, the true dimensions perfectly matches, and the diagonal line that we have obtained is a single straight diagonal line. While in case of the base factor, the diagonal line that we have obtained is a scattered line. The base factor model often underestimate the dimensions. Thus, we have understood that CRP is not only more accurate but significantly faster, because it does not require running the model multiple times for every possible value of k. Also, we saw in the quantitative structure and recovery that we were 70% of exact recovery we have obtained. 70% of exact recovery which we have obtained, which is a great result. And the previous that we have seen evaluation strategy, that when the data we are having overlapping rows and columns, after that the hierarchy which was obtained was the hierarchy that we reconstructed the hierarchy appropriately. Now let's move ahead to the next evaluation strategy that we have is NIPS hierarchy. In NIPS hierarchy, what we are doing is, this is the final evaluation strategy which was presented in research paper. So in NIPS hierarchy, we are looking at the real world data, which is 1740 NIPS conference abstracts. In this real world data, we have 1717 or 1740 approximately NIPS conference abstracts that we have. The model discover a beautiful taxonomy. The root is full. The model discovered the beautiful taxonomy. The model discovered that the root that we have is full of function words like the, a. We'll see in the next slide what kind of tree the model obtained. This is the kind of final tree that the model obtained. So the root is full of words like the, of, a. It then branches into two major research clusters that we have, which are neuroscience or machine learning. So machine learning, we have topics or words we can say like algorithm, learning, training, method. While in neuroscience, we have neurons, visual, cells, cortex. Then further, the model isolates into niche specific topics like synapses design or reinforcement learning. In case of machine learning, this was all done unsupervised. The model learned the structure of the scientific field just by reading the paper. Here we have not provided the number of topics. This was entirely based on the data. The model constructed this hierarchical structure scientific of this scientific field just by reading the data, research paper or data that we have. Now let's move toward the conclusion and let's move toward the result insight first, then we will move toward the conclusion. So um, so in the result insight, we can see that in even if a document which is initialized in wrong branch that we saw previously. We were having overlapping horizontal and vertical rows. We were getting accurate hierarchical mapping. Or even if the document is initialized in a wrong branch, then the Gibbs sampler eventually resets it into a correct path as the global topic stabilizes. So Gibbs uses some amount of iteration, let's say 10,000 iterations, to get the stability, and once it stabilizes, then it gives the correct result. Apart from that, our model also performs automatic denoising, which is shifting the noise or the common words that we have to the root. Then we have infinite scalability. The NCRP grows with the data. So we have no restriction here we have no restriction that the new data should follow the topics which were present earlier. The data can create their own topics. The data NCRP can create a new branch, and this model is able to perform non-parametric way when the number of clusters are not mentioned. In our example, we saw the number of topics. In the code demonstration also, we saw that the number of topics was not mentioned. The model itself understood that the number of topics that we found was 96, while the log likelihood was minus 8.43. So here the topics that we have obtained was 96 after training the model. So this was done by the model on its own. It automatically found this. And the NCRP, the nested Chinese restaurant process that we have, it grows along with the data, creates new branches as different variety of the data that comes. So it does not restrict the data to follow the specific topics which were introduced or which was mentioned earlier. Now moving towards the conclusion of the topic, by treating hierarchy itself here as a random variable, we allow data to tell its own story. The non-parametric approach that we have is the future of ever-growing digital corpora. So nowadays we don't have a fixed corpus or corpora that we have ever-growing corpora. So for such dynamic size corpora, our non-parametric approach is the best approach that we have. Statistical mechanics, we have seen that it balances the level of counts and the word counts. And the HLDA is more than a classifier. It is a way to see the thematic genealogy of information in a unsupervised and non-parametric form. Why it is unsupervised and non-parametric form, we have seen, because we do not specify the number of topics. It allows the data to grow. NCRP works really well even if the data that we have grows. It performs shifting of the noise to the root. So that is why this non-parametric approach is the future of managing our ever-growing digital corpora. So I end my presentation here. Thank you very much for listening.
Hello everyone. Today we are diving into a foundational milestone in natural language processing. The presentation is titled Efficient Estimation of Word Representations in Vector Space. It is based on the seminal work by Thomas Micallef and his colleagues at Google. This research fundamentally changed how machines read and understand human language. To understand why this is important, we must look at how NLP functioned before this breakthrough. Traditionally, computers treated words as atomic units. In a computer's dictionary, every word was essentially just an index or a unique ID. This created a massive problem. The computer had no way of knowing that run and jog were related. They were just two different numbers in a list. There was no inherent notion of similarity. The vision presented by Mikolov and his team was to move away from these static labels and towards distributed representations. In this new world, words are represented as high dimensional vectors. Imagine a word not as a single number but as a point in a 300 dimensional space. Words with similar meanings would naturally cluster together in this space. The core achievement of this specific paper was its sheer scale and efficiency. The authors developed a method to learn high quality word vectors from a massive dataset of 1.6 billion words in less than a single day. This was unprecedented at the time and paved the way for modern large language models. In the introduction of the paper, the authors discuss the history of large language modeling. For a long time, the dominant approach was the n-gram model. An n-gram model is essentially a sequence of n items from a given sample of text. For example, a 2-gram looks at pairs of words to predict what comes next. It is also called bigram model. The fascinating thing about n-gram models is their relationship with data scale. Simple n-gram models, when trained on trillions of words, often outperform high complex, intelligent models that are trained on much smaller datasets. This led to a brute force era of NLP, where the solution to every problem was simply more data. However, this scaling has a ceiling. While we have trillions of words available for general web text, many specialized domains suffer from a lack of data. For example, in automatic speech recognition, we might only have millions of words of transcribed audio. In machine translation, we might only have a few billion words for specific language pairs. In these scenarios, simple scaling fails. To make progress in these data constrained fields, we cannot rely on brute force. We must use more advanced techniques like neural network based language models. To illustrate why we need vectors, let's look at a real world example of how a computer sees words. In a traditional simple index system, every word is a unique entity. Think about the words dog, puppy, and spaceship. To a human, dog and puppy are almost the same thing, while spaceship is completely unrelated. However, in an atomic index system, the distance between dog and puppy is exactly the same as the distance between dog and spaceship. They are just unique labels with no mathematical relationship. This is a fundamental failure of understanding. We need a system where the words like dog and puppy are mathematically close. By representing words as vectors, we can calculate the distance between them using cosine similarity. In a vector space, the dog vector and the puppy vector would point in nearly the same direction, while the spaceship vector would point something entirely different. This mathematical closeness allows the machine to generalize if it learns something about a dog and it can reasonably apply that knowledge to a puppy. As we discussed simply, adding more data to simple models isn't enough. Word similarity is not just about words appearing in the same sentence, it goes much deeper. It captures complex relationships through simple algebra. The most famous discovery of this research is the ability to perform vector arithmetic to solve analogies. The researchers found that if you take the vector for the word king, subtract the vector for man, and add the vector for woman, the resulting vector is very close to the vector for queen. This indicates that the model has not just learned these words as related, but it has actually captured the concept of gender and royalty as directions in space. This magic of vector arithmetic proves that the model is capturing the underlying structure of human thought and language. The paper categorizes word relationships into two main types, syntactic and semantic. Syntactic relationships are basically dealing with the grammar and structure of the language. For example, the relationship strong is to stronger as quick is to quicker. The model learns that there is a specific vector direction that represents the comparative form of an adjective. Second is semantic relationships. This deals with the meaning and the real world facts. For example, France is to Paris as Germany is to Berlin. Here, the model learns the capital city relationship. The ultimate goal of the Word2Vec architecture is to maximize accuracy in capturing these relationships while minimizing computational complexity. If a model takes a year to train, it isn't useful. The breakthrough here is finding the sweet spot between a model being smart enough to understand these analogies but simple enough to train on billions of words quickly. Here are some examples of the semantic and syntactic relationships on the basis of common capital city, currency, city in state, man, woman, opposite, comparative, superlative, present participle, adjective to adverb, past tense, plural nouns, plural verbs, and so on. To understand why the new models CBOW and Skip-gram are so effective, we first have to understand how we measure the cost of training a model. The authors provide a universal formula for computational complexity. It goes by O equals to E times T times Q. Here E is the number of epochs, which is the number of times the model sees the entire training dataset, typically ranging from 3 to 50. T is the total number of words in the training set, which can be over 1 billion. Q is the complexity per word. This is the model specific calculation cost for each individual word. The authors identified that in previous models, the bottleneck was the nonlinear hidden layers. While these layers make a model complex, they are incredibly expensive to calculate when you are dealing with billions of words. The goal was to reduce Q so that T, the amount of data, could be increased significantly. Let's look at the standard feed-forward NNLM. This architecture consists of four main layers: input, projection, hidden, and output. Here is how it works step by step. N previous words are encoded, which is the context. These words are projected to a projection layer P. The data is then processed through a hidden layer H, which usually contains 500 to 1000 units. The complexity formula for this model is Q equals to N times D plus N times D times H plus H times V. The problem is the middle term N times D times H. This represents the hidden layer processing. For example, you have a context of 10 words where n equals to 10 and a vector size of 100 which is d equals to 100 and a hidden layer of 1000 units where h is equals to 1000. You are doing a 1 million calculations of just one single step. This primary computational drain makes it impossible to scale to trillions of words. To solve the fixed window limitation of feed-forward models, where the model can only say n words back, researchers developed recurrent neural networks. In an RNN, there is a recurrent matrix that connects a hidden layer to itself. It allows information from the past to be represented by a hidden layer that updates every time a new word comes in. In theory, an RNN can remember things from the very beginning of a sentence. The architecture is simpler in terms of layers: input, hidden, and output. This lacks a projection layer. However, the complexity formula is still daunting. Q equals to H times H plus H times V. The bottleneck here is H times H term. These hidden to hidden layer connections are computationally expensive because every unit in the hidden layer at time t is connected to every unit in the hidden layer at time t minus 1. While powerful, this makes RNNs very slow to train on massive datasets. Now comes the breakthrough, where the authors decided to explore simpler log linear models. These models might be less intelligent per word, but because they are so efficient, they can be trained on much more data, which ultimately makes them more accurate. Their two-step philosophy was: at first learn continuous word vectors using a simple model first, and then use these high-quality vectors as input for more complex models later if necessary. This simplicity allows for parallel training. Using frameworks like dist belief, they could run hundreds of model replicas simultaneously, slashing training time from weeks to hours. The first of the two architectures is the continuous bag of words or CBOW model. The goal of CBOW is to predict a middle word based on the surrounding context words. These are two key differences between CBOW and the older NNLM. Here, the nonlinear hidden layer is removed and the projection layer is shared for all words. It is called a bag of words because the order of words in the context does not matter. The vectors of the context words are simply averaged or summed together. This removes the n times d complexity from the hidden layer and replaces it with a much simpler calculation, which is q equals to n times d plus d times log 2 base v. By removing the hidden layer, CBOW becomes incredibly fast, allowing it to swallow billions of words and learn the relationships between them through sheer exposure to context. Here is a workout example of CBOW. So, to truly understand, let's walk through a concrete workout example using a simple sentence: the quick brown fox jumps. In this scenario, our objective is to predict the target word brown by looking at its immediate neighbors. The process begins with the input stage. We define a window of context, for instance, selecting the two words appearing before the target, the and quick, and the two words appearing after, fox and jumps. Each of these four words exists in our vocabulary as one hot encoded vector. But for the model to process them, it performs a vector lookup. It retrieves the specific d-dimensional vector for each context word from a shared weight matrix. Next comes the aggregation step. Unlike older neural models that concatenated these vectors, making the input size dependent on the window size, CBOW simply computes the average vector of these four inputs. This is why it is called bag of words. The spatial order of quick versus fox is lost. Only their collective meaning remains. Finally, this single averaged vector is passed to the output layer for classification, where the model attempts to identify brown as the most likely word to fill that central gap. While CBOW uses context to find a word, the continuous skip-gram model uses the exact opposite. It uses a single current word as the input to predict the words that are likely to appear within a certain range or window around it. The architecture introduces a critical variable, the range vector c. As we increase this range, the model looks further into the past and future of the sentence. This significantly improves the quality of the resulting word vectors because the model learns the broader topic associations, but it also increases computational complexity. A clever optimization used here is the weighing of distance. The researchers found that words very far from the target usually carry less relevant information than immediate neighbors. Therefore, distant words are sampled less frequently during training, giving them less weight in the final vector calculation. The complexity formula for skip-gram is defined as q equals to c times d plus d times log 2 base v, showing that the cost scales linearly with the window size c. Let's apply the skip-gram logic to our example sentence: the quick brown fox jumps. Suppose our current word WT is brown. The model first determines the window, which is C. If we set a maximum distance of C equals to 5, the model doesn't always look at all 5 neighbors. Instead, it randomly selects a number R between 1 and C for each training step. If R equals to 2, the model sets its sights on two words before and two words after brown. This creates four distinct classification tasks. Input brown is predicting the word the and quick and fox and jumps. By forcing the vector for brown to be good predictor for all these different neighbors, the model ensures that brown captures a multifaceted meaning that reflects the common usage in language. Now let's look at some code demonstration. In our first code cell, we move away from treating words as atomic units. We start by defining a specialized corpus that includes sentences like the quick brown fox jumps over the lazy dog and a fast brown puppy leaps over the sleepy bound. This is designed to give the model a chance to learn that dog and puppy appear in similar contexts, the first step towards making them mathematically closed. The critical transformation here is the creation of the word to mapping. In traditional NLP, this index was the end of the road. However, in this implementation, the index is merely a coordinate used to look up a high dimensional vector in the embedding system. By setting embedding equals to 10, we are creating a 10-dimensional vector space where each word will eventually find its home. This follows the universal formula where the number of words t and the complexity per word q determines our training efficiency. Now the second cell implements the continuous bag of words architecture. The code explicitly follows the paper's breakthrough strategy, removing the nonlinear hidden layer. Notice the class structure when we have an embedding layer and an n linear layer, but nothing in between. In older NLP models, a hidden layer H would have created a massive computational drain. In our code, the forward function performs the bag of words step by calling torch main embed dimension equals to 0. This mathematical averaging confirms why the order of words doesn't matter in this model. The vectors are simply averaged into a simple representative context vector. This reduces the complexity queue significantly, allowing the model to scale to billions of words mentioned in the research. Moving to the third cell, where we are implementing the continuous skip-gram. If CBOW is something soothing, the context to find a word, skip-gram is about using a single word to predict the surrounding environment. The code architecture remains non-log linear, but the data preparation changes entirely. We define a range vector C. In the script, we use a window where r equals to 2. The model performs four separate classification tasks for a single input word. For example, if the input word is brown, the code sets up a task to predict quick, the, fox, and jumps. While this increases the number of calculations per word compared to CBOW, the paper notes that this architecture is far superior at capturing semantic relationships such as king minus man plus woman equals to queen analogy. Moving to the fourth cell, which brings the theory of computational complexity into a functional loop, we use cross entropy loss and optimal SGT. In the actual paper, the authors used this belief framework to run hundreds of these loops in parallel. The loop iterates through epochs. Each time model backward is called, the gradients are updated using AdaGrad, which adaptively adjusts the learning rate. In a large scale setting, we would replace the standard output layer with an hierarchical softmax, which is a Huffman binary tree. This code demonstrates the logic that instead of evaluating every word in the vocabulary V, for every step we are optimizing the weights so that the target word vector becomes the most probable match for the given context. Moving to the final cell is where the magic happens. Once the model is trained, we extract the weights from the embeddings layer. There is no longer just random numbers, they are coordinates in a meaningful space. By using torch cosine similarity, we are proving the model's success. If the training was successful, the distance between the vector dog and puppy will be smaller than the distance between GOG, and spaceship. This allows us to perform the algebraic transformations mentioned in the paper, such as capturing syntactic relationships, strong to stronger, and semantic ones, Paris to France. In a standard neural network, the final output layer is a softmax function. If the vocabulary V has 1 million words, the model has to calculate 1 million different activations every time it makes a prediction. This is the primary bottleneck that makes training slow. The solution introduced a hierarchical softmax. Instead of a flat list of words, the vocabulary is represented as a Huffman binary tree. In this structure, every word is a leaf node. To predict a word, the model doesn't evaluate all V outputs. It only evaluates the path from the root of the tree to that specific word's leaf. Mathematically, this reduces the complexity from V to roughly log 2 base V. Furthermore, because it uses a Huffman tree, more frequent words are assigned shorter paths, speeding up the process even further. For a vocabulary of 1 million words, this clever data structure produces at least 2 times speed up in overall evaluation. Efficiency isn't just about clever math, it's about hardware and infrastructure. The researchers implemented these models on DistBelief, a large scale distributed framework developed at Google. DistBelief allows for models parallelism. It runs multiple replicas of the same model, often 50 to 100 times at the same time. These replicas don't work in isolation, they synchronize their learning through a centralized parameter server. The optimization algorithm used is mini-batch asynchronous gradient descent paired with AdaGrad, which is an adaptive learning rate. Because it is asynchronous, different replicas can update the central knowledge, which is the parameters, without waiting for each other, maximizing the utilization of thousands of CPU cores and allowing the model to process billions of words in hours. Now, how do you know that if these vectors are actually good? The authors created a rigorous test suite consisting of 8,869 semantic questions and 10,675 syntactic questions. A crucial detail here is the strictness of the test. A question is marked correct only if the closest vector found by the model is an exact match. If the model suggests a perfect synonym but not the exact word required, it is counted as a mistake. The results revealed clear strengths and weaknesses for each architecture. RNN LM, which gave excellent syntactic tasks but surprisingly poor at semantic tasks. CBOW performed better than the older NLM at grammar and roughly equal in meaning. Skip-gram is the clear winner for semantic accuracy, achieving 55% in certain tests where CBOW only managed 24%. This proves that predicting context from a word is a more powerful way to learn meaning than the other way around. Here are some examples of the model performance accuracy. Here we can clearly see that Skip-gram outperformed all other models. The true intelligence of Word2Vec is revealed in how it discovers relationships. These are not programmed by humans, these are discovered by the model by analyzing word co-occurrences. The core concept is that relationships are requested as constant offsets in the vector space. By subtracting two vectors, man from king, and adding the result to the third, woman, the model travels across the vector space to find the logically corresponding word queen. One interesting finding mentioned in the results is the accuracy boost. The researcher found that if they used 10 examples to form the relationship vector instead of just one, the accuracy of the analogy jumped by about 10%. This suggests that the direction of relationship like capital of becomes clearer and more stable as the model averages more instances of that relationship. Visualizing learned categories. This paper provides diverse examples of the model's learned across different domains. These aren't just cherry picked, they represents the systemic organization of the vector space. Here in the category geography, Athens is to Greece as Oslo is to Norway, whereas in grammar, apparent is to apparently and rapid is to rapidly. And in case of general knowledge, Einstein is to scientist as Picasso is to painter. These examples shows that the model understands capital cities, adverbial transformations, and even professional categorization. It captures word knowledge and linguistic rules simultaneously without being explicitly told either. To prove that these vectors are useful for more than just simple analogies, the authors conducted a case study using the Microsoft Research Sentence Completion Challenge. The challenge consists of 1040 sentence where one word is missing and the model must choose the correct filler from five possible candidates. The Skip-gram strategy for this task was ingenious. They used a 640 dimensional model trained on 5 million words. For every candidate word in the multiple choice list, the model predicted all other words in the sentence. The model then calculated the sum of these individual prediction scores. The word that was most compatible with the sentence rest of the context was mathematically speaking was chosen as the winner. The impact of Word2Vec was immediate and measurable across several benchmarks in NLP. For example, the researchers saw a massive 50% increase in Spearman's rank correlation, a standard measure for how well a model's similarity scores match human intuition. Another is fact verification because the model captures relationships like company CEO or state or city state. It allows for the automatic extensions and verification of facts. Another is foundational meaning, where perhaps most importantly, it provided a robust foundation for meaning, giving every downstream AI task like semantic analysis or summarization for a high quality starting point. In conclusion, the Word2Vec paper proved two revolutionary points. First, that high quality vectors are possible without expensive nonlinear hidden layers. Second, that these new architectures can scale to trillions of words and essentially unlimited vocabularies. Word2Vec successfully transformed words from static, isolated labels into dynamic building blocks for AI. It proved that meaning could be represented as location, setting the stage for the modern era of deep learning and massive transformer models we use today.
Hello, in this presentation, we will summarize the research paper GloVe, which stands for Global Vectors for Word Representation. Major topics covered in this research paper were first, goal of GloVe, which arose from the core problems from previous models. Then we will move on to the basic mathematical foundation, that is the ratios of co-occurrence probabilities. Then we will derive the mathematical objective function for our main model GloVe, and we will then proceed to show why GloVe is better than the other models along with its evaluation metrics and results obtained, finally concluding the paper and model parameters. The goal for GloVe. The core problems from previous models were very generic. There were two major models that were used. First was global matrix factorization, which was LSA, and second was local context window methods, which was Skip-gram as an example. We will look into detail for both of these models. First, global matrix factorization. Now, this model was built on a matrix that counts how often the word appears in different documents or near other words. That means it summarized in a very efficient way the global statistics of the whole dataset, which was a very major strength for this model. Although this was also a weakness because of the global statistics convergence, it often struggled with specific word relationship capturing like analogies or word similarities, etc. As for the local context window models like Skip-gram, these suffered with exactly opposite problem. Here, we can capture the context of the neighboring words using a sliding window approach, which usually surrounds immediate 5 to 10 neighbors. The strength was that it captured semantic patterns, while the weakness was the exact same strength that was obtained from LSA, that is, the global statistical coverage. Hence, the goal of GloVe was to create a model that combined the best of both. That is, we should have the global statistical efficiency from LSA as well as the contextual methods from Skip-gram. Moving on to the base mathematical approach, it was ratios of co-occurrence probabilities. Let's say we have two words I and J. For referring or for looking at the relationship between these two words, we used to one probability, which was conditional probability, that can be written as Bij, which shows if I have the word I, what is the probability J will relate to that or J will come after that, and same goes for J given and I should come after that. But it was seen that this probability does not capture meaning. This is because it just shows how similar or how go along the words are with each other. That is, what is the probability that they can be placed next to each other. But it does not capture the semantic meaning. The researchers show that this ideology can be very nicely implemented using the ratios of these probability. In the research paper, this example is shown by two target words which are I and J with ice and steam respectively. And the paper states that we should take K test words or a test word K, which is also known as probe word. This is a table from the research paper where K equals to solid, gas, water and fashion are probe words, while that K is used to generate the probability where Pk given ice and Pk given steam are calculated and given, and then we will calculate the ratio. We can easily see these ratio vary in very large scales. This is very high, this is very low, while these two are near 1. Let's move on to see the significance of these. For large ratios, we can see that the numerator is more meaningful than the denominator. While when it is small, the denominator is obviously more meaningful to the context word or the probe word K rather than the numerator. Verifying this from the example, we can see that when K given ice and K given steam were put in a ratio and K was equal to solid, the ratio was higher than 1, which means that ice is relating to solid more than it's relating to steam, which is logically verified. Same for gas, the denomination was very low, that means gas was more relating to steam rather than ice, which is also verified. While for the ratio which was near 1, we can see that it was for both words water and fashion. Now, this means words like water which are related to both target words or fashion which are related to neither target words, both will give out a ratio 1. Hence, this ratio effectively cancels out noise. This noise, that means the words that are either too common or totally irrelevant, leaving only the properties specific to the target words. Now, derivation of the mathematical objective function. Here, we will use a reverse engineering procedure. That is, we will assume and we will allocate the word vectors automatically, and then we will utilize the objective function to converge it into a better way such that the convergence error gets low and we get a very nice word vector representation. The basics that should be known for this are that we have a word count matrix X. Xij represents the time words J occurs in the context of word I. In the context of word I, we should remember this. Then Xi is the total number of times any word appears in the context of word I. That is mathematically a summation of a whole row, which can be written as summation of k of xik over all the k's, that is all the cells in that row. Pij is p given pj given I, which is xij given xi. This is a normal traditionally used conditional probability formulation. As seen previously, the best meaning is captured by the ratio of these probabilities, that is pik upon given pjk. We have to somehow convert this ratio into vector representation. Let's see how that is done. The goal is to design a function f that takes word vectors and outputs that ratio. That is, as I said before, we will assume that we already have 3 word vectors. Somehow, we will convert these word vectors into their best format so that the error between RHS, that is this, and LHS, that is these vectors, will be the least. Now, this curved line represents that the word that are we talking about right now is the context word. Hence, this K is the context word. While we see that WN and WJ do not have any curved lines above them, which shows that they are target words and not context words. Now we know that the vector space is linear. Hence, the first step to converge this towards the RHS should be that we should take the difference between the word vectors. Then we can clearly see that this is in a vector space while this is scalar. Converting a vector space into a scalar quantity calls for transposing and then taking a dot product. Hence, this is now a scalar quantity just like RHS. Now, we want subtraction to be represented as division in RHS. Two of functions are good to go with this type of arrangement. One of which is exponential, second could have been logarithm as well. We over here utilize exponential. When we take exponential of this whole, we see that this numerator obtained can be computed with the numerator of RHS, which is why here we obtain exponential of Wi transpose Wk equals to Pik. Expanding the probability as seen before using the given original formulation of Pik, we replace this and substitute the following formation over here, transposing the exponential to the other side, converting it into log. Let's move ahead. Now, we see that this log xi is not in context with the context word k. It is just a vector word representation of just the target. It does not capture any context. Hence, we have to get rid of this. So, we replace this with biases, which are bias of the target word and bias of the context word. Now, this gives us, when converted into a least square regression, will give us our weighted least square regression objective function, that is LHS minus RHS whole square and summation over all words over the vocabulary. This is the objective function for GloVe. Now you must be wondering about this extra term. This extra term is the weighing function. This weighting function significance is shown in the next slide. About the components of the objective function, we already know the summation ij to v means that it is summed over all the word pairs of the document for the whole vocabulary. The weighing function will be explained further. I will let you know about this. Then this is the major error function which we derived from here. Let us move ahead. Significance of the weighting function. In this function, it helps us to give importance to the important word pairs only. It gives less importance to lesser pairs, which can be rare pairs as well as very frequent pairs. Rare pairs are usually words that only meet once, which can be noise that can be caused because of a spelling error maybe, or any other grammatical mistake, which is why they should not be weighted much more for the model training. Whereas very frequent pairs like I am or of the, these appear very frequently in many documents. Which is why training upon them could lead for the model to be undertrained and not give very nice vector outputs. That's why these two kinds have lesser weighting function, while other pairs which focus more on target words have higher weighting function. Why GloVe is better than other models? GloVe is significantly better than other models because it has non-zero training. That is, let me explain about the LSA training and skip-gram training. We know that LSA is trained on full V square matrix. That is, it should deal with a lot of vocabulary in order to get trained. Whereas when training for skip-gram, we know that it scans word by word the whole corpus. That is, let's say if you have 6 billion words in a corpus, it will give 6 billion iterations, which is why they are both very slow. But GloVe trains only on the non-zero elements of the co-occurrence matrix X, because this is the only kind of pair which is used for training, which is valid for training. Hence, this helps us in engroning the 70 to 95% of the matrix that is typically empty, that has zero words. Because so many times there are instances where two words in a vocabulary may not appear next to each other very often, when one word J that we were considering is not in the context of the word I. Hence, the matrix is majorly empty, and our model GloVe ignores these empty cells and focuses better on the filled cells. By ignoring these empty cells, GloVe skips the vast majority of the computational work that traditional matrix models would get down in. Superiority to Word2Vec. As we saw and as I said earlier, skip-gram's traversal is 6 billion tokens. If it has, then it has to take 6 billion passes or iterations. The GloVe method working algorithm is much better than that, because it only trains on non-empty cells, not the total number of words in the book or the document. Summary table, the scaling comparison as to the older two methods, whereas for GloVe, we can see that 3 models are taken and 3 parameters for judgment are taken, which are scaling factor, data usage, and complexity. Scaling factor counts upon for LSA that the vocabulary size fully, which is V square, while as for window models like Word2Vec, skip-gram, it is corpus size C, while for GloVe it is a very efficient non-zero matrix entries only. About the data usage, we know that this takes on global counts and contains global statistics, while this only covers local windows. This, as we've seen earlier, obviously covers context and also covers global counts. For complexity, it works in big O of V square, worst case, that is every cell in the matrix is full, or at least because of maybe grammatical mistakes there is at least one entry in cells, or major cells are full. For window models, it is big O of C, where C denotes the number of words in corpus or the corpus size. For GloVe, it is proven in the research paper that it is big O of C power 2.08, which is significantly lesser than both these methods. I hope it's clear. Now let's move to the next slide. Evaluation metrics. The paper was majorly tested on 3 kinds of evaluation matrices. It was word analogies, word similarity, and named entity recognition. Word analogies. We will see what word analogies means. This was the primary focus of the paper. The primary focus of the paper, because it has a major importance in AI working environments, whereas we should be able to capture meaningful substructures and the vectors of those words should be able to show the same. The example that was used in the research paper was, we need to find a word X which is to Berlin just as Athens is to Greece. Thus, GloVe model will help us find this. To find the answer, the model takes the word vector for Berlin, subtract Athens, and adds Greece. This is how a linear analogical arithmetic works in NLU. The results obtained. The results obtained achieved 75 overall accuracy on 42 billion token corpus. This was very high as compared to the other dimensional models. It was significantly outperformed SVD based models and the Skip-gram models from the Word2Vec when trained on the same amount of data. Let's remember, same amount of data, which shows that data was not a point of variance. Hence, GloVe obviously performed much better. With a 300 dimensional vector trained on 6 billion tokens, GloVe hit 71.7% accuracy while Skip-gram hit 69.1% only. This is showed in the research paper tables that were present as results output. Word similarity. This was also a task which shows how models' distance between words matches human judgment. Similar words, as we already know, should have closer looking vectors. The metric that was used for this was Spearman rank correlation on various datasets. The results obtained were, it outperformed models trained on twice the amount of data. This time it was twice the amount of data. It beat a 100 billion word CBOW model only using 42 billion tokens. Next was named entity recognition, NER task. To show that the obtained vectors are useful for actual AI applications, they were plugged into an NER system. NER system is something that identifies names, places, and organizations in text. This is a very useful function for a model to learn and to bifurcate between words and its understanding. The metric used here for judgment was F1 score. The results obtained were, GloVe vectors provided superior features, beating all other word vectors methods almost every benchmark. We can see the proof in the research paper result tables. Conclusion about the model parameters and results. The vector size. This slide concludes the kind of parameters that fit best with our model GloVe. Now first talking about the vector size. The vector size means what should be the best dimension for a vector to work better with GloVe. Performing on various dimensions, it shows that performance improves as vector gets larger, but it also starts to level off, as in it starts to wear off in results after about 200 dimensions. This shows that if we take very large vectors, it's going to produce a lot of noise in the vector dimensional. It will start to gather context which is maybe not in that much relation to the word, and about many frequently appearing sidelined words, which is why a 200 dimensional performed the best. Talking about the window size for capturing the neighborhood, the different sizes of window defined different kind of context capturing. Let's assume that. So, small windows that were around two words, just one word behind and front, these were better for syntactic tasks, something like grammar, verb tenses, and these kind of corrections. Because we know that usually when a person makes a grammatical error, it has to be one word before or one word after, or else the grammatical mistake would be in reference to a very different word, which is why a smaller window of two words is helpful for catching these kind of errors. While the larger windows, let's say up to 10 words, were better for semantic tasks like gathering meanings and facts, more like what kind of document was this, or what hierarchy did it belong to, or what main focus in the NER system should be shown about the document, and these general concepts are spread out across sentences. So, conclusion about the paper was, GloVe successfully captures the meaning linear substructures of prediction based methods. Yes, we already have acquired this and proved this while utilizing the statistically efficient of count based methods efficiency of count based methods. We also saw that it also covers global prospect just like LSA. It significantly outperformed existing models across analogy, similarity, and NER task, the three evaluation metrics that we saw. Hence, we can conclude that GloVe was a really good model that was produced by the scientists of Stanford University, and it was a high research of that time. I was really obliged to know about this paper, and that is all about it. Thank you.
Good morning, everyone. My name is Suparni, and I shall be presenting the paper on BERT, which is pre-training of deep bidirectional transformers for language understanding. So, language model pre-training has been effective in improving many natural language processing tasks. These tasks can be divided into sentence-level tasks such as natural language inference and paraphrasing. And these tasks aim to predict the relationships between sentences by analyzing the sentence all at once. Another type of task is token level tasks, such as named entity recognition and question answering. Here, the models are required to produce a fine grained output at the token level. So, existing strategies for applying pre trained language representations for downstream tasks include the methods of feature based prediction and fine tuning. The existing standard language models are unidirectional, and this limits the choice of pre training architectures. For example, a left to right architecture is used in OpenAI's GPT model. Here, every token can only attend to previous tokens in the self-attention layers of the transformers. These, this method is not optimal for a sentence level task, and this can be inefficient while applying fine-tuning based approaches such as question answering, since these tasks require context from both directions. In this paper of BERT, the model BERT is proposed, which is bidirectional encoder representations from transformers. BERT can solve the previously mentioned unidirectionality problem by using a masked language model or MLM pre-training objective. Here, this is used to fuse the right and left context, and this solves the problem of unidirectionality. Additionally, a next sentence prediction task is also used to jointly train the text pair representations. In masked language modeling, a number of words in the input are randomly masked, and the task is to predict the word according only to the context. In the next sentence predictions, two sentences are given, and the model is asked to predict whether the second sentence follows the first one or not. During the experiments conducted, BERT received a state-of-the-art performance on a large number of sentence and token level tasks. This brings us to the model architecture. So here the input embedding is denoted as E. The final hidden vector of the CLS token is denoted as C, and the final hidden vector is denoted as Ti. Here. Each downstream task in BERT is fine-tuned. Each downstream task has separate fine-tuned models, and these are initialized with the same pre-trained parameters. In the BERT architecture, a stack of transformer encoder layers are used with self-attention to capture the bidirectional context. BERT, unlike a normal encoder-decoder architecture, is an encoder-only model. The attention is calculated as the softmax function of the product of the query and transpose of the key matrices and divided by the dimensionality of the key matrix and the value. The results can be reported on two model sizes in this paper, which is BERT base and BERT large. Here in BERT base, the number of layers is 12 and in BERT large it's 24. The hidden layer size is 768 and 1024 for both the models, and the number of self-attention heads is 12 and 16. And there's a significant difference in the number of parameters for both the models. Coming to a small implementation of the BERT model, here for the self-attention, this is calculated using the query key and values as input, and the attention score is calculated by matrix multiplying the query matrix and the transpose of the key matrix. And this is divided by the dimensionality of the key matrix. And the final attention score is returned by multiplying the weights with the value matrix. Coming to the input and output representations of the BERT model, the input representation in BERT can properly represent both a single sentence and a pair of sentences without ambiguity. A sentence can be considered a random span of continuous text rather than an actual meaningful sentence. A sequence refers to the input token sequence, and this can be one sentence or a number of sentences packed together. For the BERT model, word piece embeddings are used with a 30,000 token vocabulary. Here, the first token of every sequence is always a classification token labeled as CLS. And the final hidden state corresponding to this token is used as the sequence representation. And this is used in classification. The sentence pairs are packed in a single sequence, and these are separated by a separator or sep token. And a learned embedding is added to each token, indicating whether it belongs to sentence A or sentence B. And for a given specific token, the input representation is calculated by summing the embedding of the corresponding token, the segment embedding, and the position embeddings for that token. Coming to an implementation. Here, this code cell shows the implementation of the token embeddings for the input sequence in BERT. Here, the token embedding is calculated using the neural network embedding function, and the same is done for segment embedding and positional embedding. Here, this function defines the input sequence for the BERT, and here, the three variables are initialized for the three kinds of embeddings, and the input sequence that is returned is the algebraic sum of the token, segment, and position embeddings. So this is calculated by the code. This diagram shows the BERT input representation. As we can see, it contains the token embeddings, which are denoted by the actual words, and the CLS token, and the sentences are separated by the SAP token. Here, this layer consists of the segment embeddings, and these are the positional embeddings, denoting the position of each word or token in the sentence. And these three layers are summed together to form the final input representation. Coming to the pre-training tasks in BERT, the pre-training of BERT is done using two unsupervised tasks, which are described here. The first one is masked language modeling, or MLM. A standard conditional language model can be only trained left to right or right to left in one direction. If it was trained bidirectionally, each word could indirectly see itself and pay attention to itself. So the model can essentially predict the target in a multi-layered context and without any loss, which would not allow the model to train properly. So here, to train the deep bidirectional model, a percentage of the input tokens is masked at random, and the task is to predict those masked tokens based only on the context of the sentence. This procedure is referred to as masked language modeling. The final hidden vectors corresponding to the masked tokens, they are fed into an output softmax function over the vocabulary. For the BERT model, 15% of all the word piece tokens are masked in each sequence at random. And as Autoencoders can predict all the tokens at the same time. In this model, to preserve efficiency, only the masked words are predicted rather than reconstructing the entire input sequence. However, the mask token does not appear during the fine-tuning phase. So there might be a mismatch between the pre-training and fine-tuning. To solve this, the masked words are not always replaced by the mask token. 15% of the token positions are chosen for masking and prediction. And of these 15% tokens, around 80% of them are replaced by the mask token. 10% of the time, 10% of the time, a random token is used to replace the selected token, and the other 10%, the token remains unchanged. And the model is asked to predict the token that is selected. The other pre-training task used in BERT is next sentence prediction. This is used to capture the relationship between two sentences by predicting if one sentence follows the other. This task can be generated from any monolingual corpus, and while choosing the sentences A and B for each pre-training example, 50% of the time, sentence B is the actual next sentence that follows A, and this is labeled as is next. And the other 50% of the time, it is a random sentence from the corpus that is labeled as not next. And to obtain long sentences, a document level corpus is used rather than a shuffle sentence corpus. This allows longer sentence to be obtained. After the pre-training is done for BERT can be fine-tuned on BERT can be fine-tuned to adapt to specific tasks. The pre-trained BERT model is adapted to specific tasks using labeled data. To adapt it to specific tasks, a simple task-specific layer can be added on top of the pre-trained model, and the entire combined model, consisting of the original and the new layer, it's trained jointly during the fine-tuning process. For different tasks such as classification and question answering, the same architecture of the model is used across the whole time. Therefore, the fine-tuning process requires minimal changes, and a relatively small task-specific data corpus is required. And compared to pre-training, the fine-tuning is relatively more efficient. This brings us to the experiments that were conducted on the BERT model. Two major experiments conducted were the GLUE benchmark and the Stanford question answering dataset. The first one, GLUE, or General Language Understanding Evaluation, it's a collection of a large number of natural language understanding tasks. And these tasks are designed to test sentiment analysis, sentiment similarity, and natural language inference. To fine-tune on GLUE, the input sentence is represented according to the original model architecture, which is the summation of the token embeddings, segment embeddings, and position embeddings. And the output layer has minimal changes, such as a few new parameters are introduced, which are the classification layer weights and the number of labels. Here, the input format is the original, which is starting with the classification token, and the sentences are separated by the separator token. The BERT model achieves state-of-the-art results on all the GLUE tasks and demonstrates a strong general natural understanding ability. This brings us to the paper, where these are the GLUE test results for BERT. As we can see, both the BERT base and the BERT large model have performed significantly better than the SOTA model, the BiLSTM and ELMO combination, and OpenAI GPT as well. Here, the BERT base and BERT large models outperform all the systems on all the tasks by a significant margin. They have It has achieved over 4.5% and 7.0% accuracy improvement over the prior models, demonstrating the strong general language understanding ability of the BERT model. Another experiment conducted was based on the Stanford Question Answering Dataset, or SQUAD V1.1. Here, the task was that, given a question and a paragraph, the exact answer span needed to be extracted from the text. Here, the input was in the format of the CLS token, the question statement, the separated token, a paragraph, and another separated token. And this was jointly encoded. Here, the model predicted the probability distributions over the start and end token positions and predicted the answer in this way. The squad experiment achieved a 93 F1 score and about an 80 EM score. This greatly outperformed the previous systems and the human baseline. Here we have the results of the squad dataset experiment, the squad 1.1 results. Here we can see that even the BERT-based model has a significantly better performance of 88.5%, which has outperformed all the previous models, including the human baselines as well. And the BERT large model has an accuracy score of 92.2%, which is a significant improvement from the previous models. And this demonstrates BERT's strong bidirectional contextual understanding for long sentences and its ability to extract answers from them. Several other experiments were conducted, including SWAG and ablation studies. On the situations with adversarial generations or SWAG datasets, it contains 113,000 sentence per completion examples. And these are supposed to evaluate grounded common sense inference for a model. The task is that given a sentence, the model has to choose the most plausible continuation among 4 different choices. Here, BERT has significantly outperformed the prior models by leveraging the bidirectional context. By fine-tuning on the SWAG dataset, 4 input sequences were constructed, each containing the concatenation of the given sentence and a possible continuation. And the model was trained for 3 epochs, and BERT has significantly outperformed the prior models. In ablation studies, a few components such as the mass language modeling and NSP component were removed, and the impact of these changes were analyzed. And as the result, it was found that the mass language modeling, or MLM, was critical for deep contextual understanding, while the NSP was helping in task and informing the relationship between sentences. Coming to the results, coming to the overall results for all the experiments of the model, here we find that the fine-tuning the BERT model is stable and is effective across different tasks with minimal architecture changes. The larger version of BERT, which is BERT large, has consistently outperformed the smaller versions such as BERT base, which was the original model. And here, more pre-training steps and a larger data corpus can lead to better downstream performance. And BERT's specific bidirectional training enables a deeper contextual understanding compared to other unidirectional models, where attention can only be provided to the previous tokens. And BERT also shows strong generalization across the diverse natural language processing tasks. Coming to some more experimental results. This was the experimental result for SQUAD 2.0. Here we can see that the BERT large model has fairly outperformed some of the previous models, especially in the F1 score, and is second only to the human baseline. And here we have the SWAG test accuracies, and we can see that both the BERT base and BERT large models have significantly outperformed GloVe and ELMO by almost a 30% margin. and it has outperformed OpenAI's GPT by almost a 8% margin, and it has even outperformed the human expert baseline as well. Coming to a few code implementations, here we have the implementation of the token of embeddings and the input representation, and this shows the implementation of the encoder block of the BERT model. Here, the multi-head self attention is implemented, and this is the layer of the sequential layer of the neural network. Here, the self attention of the model is calculated using the matrix multiplication and transpose, and this shows the implementation of the masked language modeling or MLM pre-training task. Here, a random set of tokens is chosen, which is about less than 15% of the tokens selected. And among the selected tokens, a random token is chosen. If the probability of the random token is up to 80%, it is replaced by the mask token. And amongst the other 20%, a random other token is used to replace that token, and else the token stays unchanged. So this is the task of masked language modeling, and this is the section used to create the data for the next sentence prediction task. If the next sentence does in fact follow the previous sentence, then the label is set to 1. The isNext label is set to 1, and if it does not follow the previous sentence, the token is set to 0. And this label is returned to the original model. So in conclusion, the BERT model is unique in the way that it introduces deep bidirectional pre-training for language understanding. The pre-training tasks include masked language modeling and next sentence prediction for effective learning. The BERT model has achieved state-of-the-art results on benchmarks like GLUE and Stanford question answering dataset and multiple other experiments. A simple fine-tuning process can enable BERT to adapt to multiple diverse natural language processing tasks. And finally, BERT establishes a new standard for transfer learning in NLP by employing bidirectional context, which is a significant improvement from other models. So this brings us to the end of our presentation. Thank you.